Hello viewers, welcome to my channel Shraddha's Physics. This video is based on statistical mechanics for the core 14. Today our topic is Gibbs paradox. So what is Gibbs paradox? We'll see in detail. So before that, let us consider this is suppose a chamber. So this chamber is filled with some monoatomic gas. So if we will get partition in this chamber, then in this part the pressure, volume, temperature and the number of particles is same as that of the second chamber. So if the entropy in the chamber 1 is S1 and entropy in the second chamber is S2, that is when we are getting partition in between this chamber, and then if we want to calculate the total entropy of this chamber, then simply this is the additive property of entropy, S equal to S1 plus S2. And if we will remove this partition, and that means the ideal gas in the first chamber and second chamber get mixed. So this after mixing, what will happen to this system? So what will be the change in entropy, or what will be the entropy in this chamber now? So we can see that what is the entropy in the before mixing in this chamber and after mixing in this chamber. So we will see that there will be some difference. There will be some difference between before mixing the entropy and after mixing the entropy in this chamber. So that leads to the Gibbs paradox. So let us see what happened. So let us consider the same monoatomic gas is put in two chambers separated by a rigid partition of pressure P, volume V, temperature T and the number of particles N in each chamber. So we are considering that there is no difference between the two subsystems. So before mixing, in chamber 1, if you can remember the entropy we have calculated, that the entropy is S equal to Nk ln V plus 3 by 2 ln 2 pi m by S square minus 3 by 2 ln beta plus 3 by 2. So here you can see that. So in chamber 1, this entropy S1 will be equal to Nk ln V plus 3 by 2 ln 2 pi m by S square minus 3 by 2 ln beta plus 3 by 2. Similarly, in chamber 2, this pressure, volume, temperature and the number of particles is same. So the entropy is same. So the total entropy in this chamber will be equal to S1 plus S2. Since entropy is an extensive or your additive property, so we have to just add this entropy. So this will be this plus this, it means twice of Nk ln V plus 3 by 2 ln 2 pi m by S square minus 3 by 2 ln beta plus 3 by 2. Now we'll see after mixing. After mixing means when we will remove this partition, then after that the volume V increases to twice of V. This volume V becomes twice of V. The number of particles becomes twice of N, but the pressure and the temperature of the system remains constant. So in that condition, so the volume increases to 2V, the number of particles N increases to 2N, and here we make the pressure and temperature constant. So from this energy relation, simply what we have to do? So the number of particles is twice of N. So this will be 2Nk and the volume becomes 2V, and in place of N we have to write 2N, and in place of V we have to write 2V, and in place of beta this is 1 by kT. So there will be no change in temperature. So you have to keep it as it is. So here you can see that this will be entropy equal to twice of Nk ln twice of V plus 3 by 2 ln 2 pi m by S square minus 3 by 2 ln beta plus 3 by 2. Clear? So this will be 2Nk, this is log 2V. So this will be ln V plus this V, just a minute, see, this is log V plus 3 by 2 ln 2 pi m by S square. This is minus 3 by 2 ln beta. This is plus 3 by 2. Here you can see that this will be log 2b. It means log 2 plus log b. So this log 2 into 2nk, this will becomes 2nk log 2. Clear? So this portion, this part, the first part of it is S0. S0 means the before mixing. Here we have calculated just that is before mixing. S0 will be equal to this much. So simply we have to put that. So simply here you can see that we have put it here, that is 2Nk log B this much, whatever. So plus 2Nk ln 2. So the entropy that is in equation 1 means this S0 and 2 is not same, because here you can see that this S0 is before mixing the entropy, and here you can see that this is the extra part 2nk log 2. So that is, it is not a reversible process. If the entropy is same before mixing and after mixing, then that will be a reversible then that will be a reversible process. So this will be a paradoxical situation, or it is called Gibbs paradox. So the entropy of the combined system should not change. Here you can see that the entropy get changes by the factor 2nk log 2. So the paradox can be resolved by quantum mechanics, that is the molecules in an ideal gas are indistinguishable. So in the previous we have considered that the ideal gas are distinguishable in nature. So for that here we have get a extra part. This will be the extra part. So the molecules of an ideal gas we have to consider that they are indistinguishable, or that is the quantum mechanical particle. So in classical ideal gas we have overcounted the state by assuming the molecules to be distinguishable, and the permutation of this n molecule could lead to n factorial different state. So simply we can say that this 1 by n factorial, so we have to reduce it by 1 by n factorial. So the thermodynamical probability modified to, so we can see that this thermodynamical probability means the microstate, that is gi power ni, it will be get reduced to ni factorial. So that will be gi power ni divided by ni factorial. So in classical mechanics we have just overcounted the n permutation of n molecules, means that is we have overcounted n factorial different states. So this Sackur Tetrode relation, it derives the, that is the partition function. First of all, this is v power n divided by n factorial h power 3n 2 pi m by beta whole power 3n by 2. Here we have already calculated this partition function. So you can see the previous lecture. So z equal to this much. So this ln z will be simply, this will be n ln b, this is divided by n factorial h power 3. So this will becomes minus 1 by n ln n factorial into minus 1 by ln h power 3 n factorial. So simply after calculating this, we will get ln z will be n ln b plus this will be 3 by 2 ln 2 pi m by a square minus 3 by 2 ln beta minus ln factorial, ln n factorial. So this will be by putting the Stirling approximation, that is ln x factorial equal to x ln x minus x. So by putting this you will get n ln b plus 3 by 2 ln, this will be 2 pi m by a square minus this will be 3 by 2 ln beta minus this will becomes minus ln n ln n, this will be minus minus plus, that will be n by putting the Stirling approximation. So the next is, this will be, this is by taking common n, this is ln b minus ln n, so that will be ln b by n, log a minus b, log a minus log b equal to log a by b. So plus 3 by 2 ln 2 pi m by s square minus 3 by 2 ln beta, this will be taking n common, this will be remain 1. So the free energy will be, here you have calculated ln z, so the free energy will be equal to minus kT ln z, so that will be minus nkt, this much part. Now we can easily calculate the entropy, that is minus dou f by dou t at constant b. So from that you can solve, this is the free energy relation. So from this relation, if you will solve with respect to temperature, if you will calculate the derivative of this, so this will be, the first term will be minus minus becomes plus, this will be nk with respect to t means dou t by dou t is 1, so nk into this much, nk ln v by n plus 3 by 2 ln 2 pi m by s square minus 3 by 2 ln beta plus 1. Again you can see that in the first term there will be no temperature, there will be no term. So in the second term also there will be no term of temperature, but in the third term here you can see that is ln beta, beta means 1 by kt. So here minus nkt minus 3 by 2, that becomes plus 3 by 2 nkt ln beta. So here this minus minus becomes plus, again this is your minus, so minus 3 by 2 nkt. So this is nkt into ln beta is 1 by beta. It means 1 by 1 by kt. Again, the derivative of 1 by kt, it means minus 1 by kt square. Clear? So this is minus 3 by 2 ln beta. This is minus kt. So minus minus becomes plus. Again this is minus. So minus. This is 3 by 2 nkt. This is nkt. Ln beta is 1 by beta or 1 by kt. Since you know beta equal to 1 by kt. So here minus 3 by 2 nkt 1 by into 1 by 1 by kt into the derivative of this much dou by dou t of 1 by kt is minus 1 by k t square. So by cancelling this term you will get simply 3 by 2 nk. So the total term is nk ln v by n plus 3 by 2 ln 2 pi m by square minus 3 by 2 ln beta plus 1 plus from this term if we will take nk common, the remaining is 3 by 2. Clear? So this is nk ln v by n plus 3 by 2 ln 2 pi m by square minus 3 by 2 ln beta. This 1 plus 3 by 2, that becomes 5 by 2. This is called the Sackur Tetrode equation. This is called the Sackur Tetrode equation. The Sackur Tetrode relation also can be written as this is nk ln v by n plus 3 by 2 ln. This will becomes 2 pi m by square. This is ln beta. So that will be 1 by 1 by kt. So that will become kt. So plus 5 by 2. So this will be ln v by n plus this will be power of ln 2 pi m kt by square power 3 by 2. So this is plus 5 by 2. S will be equal to nk ln v by nh cube 2 pi m kt power 3 by 2 exponential 5 by 2. Here we have just taken common the ln. So this is nk ln. So this is the addition term. So it will become multiplication v by n. This will be s square into 3 by 2. 2 to get cancelled. So this will becomes nh cube 2 pi m kt power 3 by 2. Simply this will be taking ln common. So this will becomes exponential power 5 by 2. Clear? So this is the another form of Sackur Tetrode equation. So here, so before mixing, the entropy of the chamber is equal to the in chamber 1 will be equal to in chamber 2. So as we have seen just the previous. So S naught, that will be the total. S naught will be equal to nk ln v by n. So here I am just putting S naught prime. So that is equal to nk ln v by n plus 3 by 2 ln. This relation just here we have written. So this the chamber in chamber 1 the entropy will be equal to the entropy in the chamber 2. So the total entropy we can write. So the total entropy S will be twice of nk into this much before mixing. So again after mixing if we will calculate, so the volume V increases to 2B and the number of particles increases to 2n. So now the entropy becomes twice of nk ln. So you can see that the volume becomes 2B and the number of particles becomes 2n. So that will be 2B by 2n plus 3 by 2 ln 2 pi m by square minus 3 by 2 ln beta plus 5 by 2. So clear? Before mixing S naught will be this much. After, so in chamber 1 and chamber 2 before mixing the entropy is same. So before mixing the total entropy will be twice of this much. Since in chamber 1 and chamber 2 the entropy is same, so simply we have to just add the total, and for the total entropy we have to just add. And after mixing means when we remove this partition, at that condition the volume becomes the twice and the number of particles twice. So in that condition the entropy will be simply n will be double, v will be double, and in place of v and n we have to simply multiply 2 here. So by putting this here you can cancel 2 2. So this will becomes this. So now you can see that this entropy 2nk ln v by n plus 3 by 2 ln 2 pi m by square minus 3 by 2 ln beta plus 5 by 2. So now you can see that this entropy is same as this entropy. The equation 6 is same as this. So now you can, so why this happen? Because in quantum mechanics what we have considered, now the particles are indistinguishable in nature, so that this Gibbs paradox is resolved. Because in classical mechanics, simply we have calculated the more number of state, so that is n factorial number of state we have overcounted. So to reduce that, so by reducing this number of microstate by ni factorial or n factorial, so we have resolved this problem. Or we can see that, so as a whole, I can say that in Gibbs paradox, what we have seen, so why Gibbs paradox arises? Because in classical mechanics, as per the classical basis, we have considered simply the particles are distinguishable in nature. So because of distinguishable in nature, we have overcounted the number of particles. So we can see that before mixing, the entropy, when we get partition in this chamber, so before mixing the entropy, the total entropy of the system is not same as after mixing, or when we will remove this partition after mixing, the entropy is not same as that of before mixing. But when we will solve the Sackur Tetrode relation, when we have calculated the entropy by using this Sackur Tetrode relation, then we have seen that the entropy before mixing is same as that of after mixing. So I think this is clear. So this is all for today. That is all about your Gibbs paradox. If you have any query, then you can ask me in the comment section. So thank you all for today.